Okay, thanks very much for the introduction, and thanks very much for the invitation to speak. It's my first time in Korea, and it's been a great trip so far. The hosts have been very hospitable. So my first talk is going to be somewhat more elementary. Suyil told me that it's good if you want to increase the level of difficulty of the talk, it's better to have it like a smooth takeoff of a flight rather than a hard landing. So I'm going to try to attempt to do that. Yeah. So, all right. So I'm going to start the story today with the first and simplest example of an L function, which is the Riemann zeta function, which is just the sum as n goes from 1 to infinity of 1 over n to the s. So this converges for s, well, a real number greater than 1, or more generally a complex number greater than 1. Okay. So, and as is well known, this is taught in our calculus classes, at least for a real variable s, as you approach 1 from the right, that the limit of this function, as s approaches 1, is infinity. This is just saying that the harmonic series, the sum of 1 over n, diverges. 1 plus a half plus a third plus a fourth, that diverges. So, but more precisely, it turns out that if you approach this from the right by, if you approach zeta of s from the right, approach 1, then you multiply by s minus 1, then the limit of that actually is equal to 1. And in fact, the zeta function can be extended to a meromorphic function in the complex plane, which has a Taylor expansion that starts with 1 over s minus 1 plus higher order terms. So there's a simple pole, zeta of s, sorry. So there's a simple pole of zeta of s at s equals 1 with residue 1. Okay, so the functional equation that I mentioned can be given really explicitly. I'll try to define this, draw this c to look different than this zeta. So you complete it by introducing exactly one of these L factors at infinity that Mahesh was talking about earlier today. So you throw in, it's essentially a gamma factor, so it's pi to a power times gamma factor of s over 2 times zeta of s. Then this extends to a meromorphic function on the complex plane, which satisfies the functional equation that its value at s is equal to its value at 1 minus s. Okay? And so from this, you can deduce a relationship between zeta of s and zeta of 1 minus s, where you have various gamma factors interplaying. So this holds for all complex numbers s. Okay? And then from this equation and the behavior at s equals 1, you can apply the equation relating s and 1 minus s to give you the behavior of zeta of s at 0. And zeta of s at 0 turns out to be evaluated to be negative 1/2. So that follows directly by knowing the properties of the gamma function and this fact here together with this functional equation. Okay, so this is the first example of a special value of an L function, either this one or this one. Okay, this is the special value of the residue that I want to try to generalize today. Okay, so now let's move on to a more general situation. So now let's let f be any number field. Be a number field. So by a number field, I mean a field extension of Q of the field of rational numbers, okay, such that the dimension of f as a vector space over Q is finite. Okay, so that's a number field. And so just to give two examples that maybe I'll come back to put ourselves on firm footing, think of Q adjoining the square root of 2, which is just the set of sums a plus b root 2, where a and b are rational. Or you could think of sort of the rational complex numbers Q adjoin I, which are the set of a plus bi, where a and b are rational. So I here is the usual square root of negative 1. Okay, so these are two examples of number fields. I mean, Q itself is a number field, and then these are two examples of quadratic number fields, meaning this dimension is 2. Okay, now given a number field, we have its associated ring of integers. So given the field Q, you have the integer sitting inside of it, the ring Z. And given these fields, there are analogs, which are called the ring of integers. So I'll let OF, I'll write by OF, be the ring of integers of F. And what's the definition of that? That's just the set of elements in the field F, okay, such that X satisfies a monic polynomial with integer coefficients. Okay, so that's the ring of integers. And associated to this data of a number field F and its associated ring of integers, I'm going to define a generalization of this Riemann zeta function and try to generalize the formulas that I've told you for the value at 1 and at 0. Okay, so okay, so let's just in terms of the ring of integers, let me just say that what is the ring of integers of Q? Well, if T is A over B, which is in Q, with A and B and Z, this pen be replaced. Then, of course, T satisfies the polynomial that bt minus a equals 0. And this is sort of monic if b is 1. So basically T is in OQ, if and only if b is, well, maybe plus or minus 1, you can always.
That's if it's in the most reduced form, right?
Yeah, so these are reduced. This is reduced. Okay. So that's say that the ring of integers of Q is just Z. Now this isn't a proof. This isn't a proof because I said it satisfies some monic polynomial, but it turns out that it satisfies some monic polynomial with integer coefficients if and only if the smallest polynomial with rational coefficients that it can satisfy is already monic. So it turns out you can turn this into a proof using unique factorization. Okay, but anyways, the point is that therefore these rings of integers are, the reason they're called rings of integers is that they're generalization of the ring of integers in the case when Q is, when you have Q, the ring of integers is Z. So the ring of integers of Q adjoin root 2 is just Z bracket root 2, which is the set of Z linear combinations of A and, where A and B are integers. And similarly for the other example I gave, that the ring of integers of Q adjoin I is just Z bracket I, where it's just Z linear combinations of 1 and I. But then don't get too carried away thinking this always works, because the ring of integers of Q adjoin, do I want root negative 3, for example? It's a little bit more complicated. It's the set of A plus B root negative 3. You have to allow denominator of 2, where A and B are in Z, and A is congruent to B mod 2. Okay, so now that we have that data, we can define the associated zeta function that replaces the Riemann zeta function that I started the talk with. Okay, so I'm going to make the definition that zeta sub f, so f is now my number field. Okay, this is the sum. So now we're going to sum over all the ideals So right with a Gothic A, all the ideals of my ring of integers OF that are non-zero. Okay, so A an ideal of 1 over the norm of the ideal to the s power. Okay, where the norm of the ideal A is by definition the size of OF modulo the ideal A. Okay, so OF mod A is some ring, the quotient ring, and it turns out for rings of integers of number fields, it turns out that when A is a non-zero ideal, this quotient is always a finite ring, and its size is called the norm of A. So if I take 1 over that norm to the s power, that's called the zeta function of my field F. And I'll just point out that in the case of Z, you get exactly the Riemann zeta function, because these non-zero ideals are exactly indexed by the positive integers, and the norm of the ideal generated by n is exactly n. Okay, so now zeta f of s satisfies a functional equation relating the values at s and 1 minus s. So again, this sum converges. So this sum converges for a real part of s. Okay, for a real part of s greater than 1. And then you can extend it to the entire complex plane to a meromorphic function, relating, and there's some gamma factors again. I'm not saying they're equal, but they're almost equal. They're equal up to multiplying both sides by some gamma factors and powers of pi. Okay. Okay, so that's the basic setup. And now the question is, I want to know what is the value of this thing at s equals 0 or at s equals 1. And so that's the statement of that result is the Dirichlet class number formula. And I want to talk about that in some detail now. Okay. So this function is a meromorphic function, but its only pole is at s equals 1. It has a simple pole there. So the Dirichlet class number formula deals with the residue of that pole. But using the functional equation, you can restate it as telling you the value of the function at 0. And that's somewhat more elegant, so I'll state it that way. So this is the Dirichlet class number formula, but stated in a slightly different way than one usually finds, because I've turned the point from s equals 1 to s equals 0. So it says that the Taylor series of zeta f of s at s equals 0 starts as follows. So zeta f of s, it's a certain ratio, which I'll write hf rf over wf times s to the r. Maybe I should write rf, but I won't. I'll just write r. Okay, plus higher order terms. Okay, so now you see that it turns out there might be a zero of order r, and I have to tell you what r is. Okay, so now I'm going to spend a little bit of time telling you what the definition of all these terms are appearing in this formula: h, r, w, and r, little r. Okay, so hf is the class number of f. Okay, which is defined to be the number of equivalence classes of non-zero ideals of the ring of integers of f under a certain equivalence relation, which I'll tell you. So it's the number of equivalence classes of non-zero ideals of OF. Okay, under a certain equivalence relation. Okay, so we'll say that two ideals A and B are equivalent if there exists alpha and beta in OF, okay, that are non-zero, such that if I multiply A by alpha and b by beta, then I can get them to be equal. So they're equal up to multiplication by principal ideals. Okay, so I just want to point out that HF equals 1 if and only if OF is a PID by definition, basically. It's not quite the definition. There's a little bit of something you have to check in that statement. But basically, if A and B are automatically principal ideals, say A is represented by X and B is represented by Y, then I can take alpha to be Y and beta to be X, and then I have an equality there. So, so this class number is nothing but a measure, a concrete measure, a numerical measure of how far the ring OF is from being a PID. And one of the first fundamental theorems of algebraic number theory is that this number HF is actually finite, that there are actually finitely many equivalence classes. That's proved using a sort of geometry of numbers technique. Okay, so so I've told you one of the 4 terms I need to tell you about. So now let me tell you what R is. Okay, so R is going to be determined in terms of 2 numbers, R1 and R2. So R1 is simply the number of embeddings of my field into R, the real numbers. Okay, so for example, in the 2 examples I gave of Q adjoin root 2, it's 2, because I can send root 2 to root 2 or root 2 to negative root 2. In the case of I, it's 0, because I can't be sent, there are no real numbers whose square is -1. R2 is the number of embeddings of F into C. Okay, actually, it's not quite how I want to do it. I want to write it as it's the number of pairs of complex conjugate embeddings of F into C such that the image does not land in R. Okay, so given such an embedding, if I then post-compose with complex conjugation on C, I get another embedding. So these embeddings show up in pairs, because those 2 embeddings are different if the image doesn't land in R. So in the examples that I gave, Q adjoin root 2, this would be 0, R2, because both embeddings landed in R. Whereas in Q adjoin I, this number is just 1, because I have 2 embeddings. I can go to I or to -I, and those are complex conjugate. Okay, and then the number R is defined in terms of these just by R1 plus R2 minus 1. Okay, so the first sort of non-obvious fact about this is that the order of vanishing at S equals 0 is equal to this number, and this comes from examining the gamma factors that show up in the functional equation. Okay, now the last thing is I need to define the W and then the regulator R. So it turns out, it's called the Dirichlet unit theorem, that OF star is a finitely generated abelian group. It's isomorphic to z to the R cross a finite cyclic group of roots of unity, which is called mu of F. Okay, so a group of roots of unity. Okay, so there's a finite cyclic group of roots of unity, and its size is what WF is. So this is the size of mu of F. Okay, and so this is the same R as this R. So that's another theorem. Okay, it's the Dirichlet unit theorem. Okay, and now the thing that I really want to concentrate on, and what's going to take up the remainder of the talk, is this idea of the regulator. Okay, so that's the last term that shows up in this formula. And that's the most interesting term in the sense that the other terms are rational numbers. Everything I've defined as rational. This RF represents the transcendental part, or at least the possibly transcendental part of the value at 0, or the leading term at 0, or equivalently the residue at 1. well, the residue at 1 actually might have some extra pi power terms from the gamma factors. But all right. So, all right, let me define the regulator now. So the regulator is defined as follows. So we let V1, V2 through VR plus 1 denote the Archimedean places of F. So what do I mean by an Archimedean place? It's these embeddings. So these are called the quote Archimedean places. Okay, so there's exactly R1 plus R2 of them, which is R plus 1, which is why I've labeled them this way. So basically, for each of these complex conjugate embeddings, I've just chosen one arbitrarily, and everything I'm going to say later is not going to depend on the choice that I make of the embedding of the field into the complex numbers up to conjugation. Okay, so for each of these pairs, I just choose one of the embeddings, and I call it VI. All right, so next we let epsilon 1 through epsilon r be a basis of this group OF star modulo this finite group of roots of unity, which is just isomorphic to z to the r. So it has a basis consisting of r elements. Okay, and now RF, the definition of RF, which is called the regulator of OF, of F, or of OF star if you want. Okay, this is the absolute value of the determinant of a matrix. And the elements of the matrix, it's an R by R matrix. Okay, and it's the ijth entry is the absolute value of Vi of epsilon j. Okay, so this is as I and j go from 1 to R. Okay, now this might look a little funny because there's R plus 1 V's and I just stopped at VR, but it turns out it doesn't matter which one you take. And now also I should say, what if you took a different basis? Also, that would just change the determinant possibly by a sign. So we take the absolute value, it's independent of the choice of basis. Okay, so it's independent of all those choices. Okay, so that's the formula. So now let me just do some examples of putting that formula together with the two examples I gave, Q adjoin root 2 and Q adjoin I. So in fact, if you do the case of Q, you get, that's what I'll start with. You just get back the first formula that I told you. Okay, so first example is that F equals Q. Okay, so in this case it turns out you can prove that the class number is 1. In fact, all the examples I'm going to do today, the class number is 1. Okay, so R, the number of real embeddings, Q can go into R only in only one way, but there are no complex embeddings. So there's only one embedding of F into C. It's the one that sends F already, of Q into R. So plus 0 and then minus 1 is the formula to get 0. Okay, and that's why there was no 0 of zeta of S at 0. There was actually a number there. And by convention, when this R is 0, you have a 0 by 0 matrix. What's the determinant of that? Well, you just define it to be 1. And the number of roots of unity in Q is just 2, because there's plus or minus 1. Okay? And so then the formula that I gave is that the Riemann zeta function at 0 is negative 1/2. And that's exactly H times R divided by W with a minus sign. And there's no 0 there. So it's just, that's the number, and that's it. All right, so now let's do another example. I'll do Q adjoin I first, because in some sense it's more similar to this one. So again, the class number is 1. Okay, now the R, there's no real embeddings, right? I can never go to a real number. Okay, and there's one pair of complex conjugate embeddings. So you get 0. So again, we're just going to be looking at the value of zeta at 0. Now the regulator, again, in the 0 by 0 case, we define that to be 1. And now the number of roots of unity is 4, because we have plus or minus 1 and plus or minus I. And therefore, zeta of q adjoin I at 0 is exactly negative 1/4. Okay? Okay, but now we get to a more interesting example where this RF, this regulator term, which is actually what I'm most interested in, shows up. So let me do that on a separate board. So this is the case of q adjoin root 2. Okay, so for my third example, I'll take f equals q adjoin root 2. So again, hf is 1. The class number is a very interesting invariant of a number field, but I won't really be talking much about it in these lectures. Okay, R. So there's 2 embeddings into R. There's 0 into C that don't land in R. And then you subtract 1, you get 1. So now we get something interesting for the first time. We see that zeta of 0 is going to be 0. We're looking for the value of zeta prime of 0. Okay, so and the number of roots of unity, well, in any field that embeds into R, all you can have is plus or minus 1. So the number of roots of unity is 2. But now we get something interesting in terms of the regulator. The regulator is the determinant of a 1 by 1 matrix. So to figure out what that is, we need to figure out what OF star is. So OF star, well, it's going to be what I told you is going to be the group generated by one element, and then cross this group of roots of unity, plus minus 1. And it turns out that you can write down what the unit is. Root 2 plus 1 is a unit. Okay, so meaning that there's an element that you can multiply by it to get 1, because root 2 plus 1 times root 2 minus 1 is 1. And this is not a torsion point. That is not a root of unity. So the powers of it generate an infinite cyclic subgroup of OF star. Okay, so this RF turns out to be just the log of root 2 plus 1. Okay, so the final formula is that zeta of q adjoin root 2 of S, if Taylor's series starts by minus log of root 2 plus 1 all over 2 times S plus higher order terms. Okay, so in other words, zeta prime of 0 is equal to this number. So zeta of 0 is 0, and zeta prime of 0 is equal to that number. And those are the types of formulas that I want to generalize now. So now we can ask for generalizations. So you could ask for the values at other integers. So that's a very interesting question. Okay, but I'm actually not going to answer that question or discuss that question. I'm really going to be discussing the question of what about other L functions, and also talking about mainly about the points 0 and 1. Okay, so let me just mention some names, and this is in no way supposed to be a complete list, but some of the prominent names of people who have made proven theorems or stated conjectures about values, special values of L functions at other integers, or for other L functions, or for other L functions at other integers. So Borel studied this, and in fact gave a very interesting interpretation of the values of the Riemann zeta function at other integers. It's also studied by Beilinson, by Bloch and Kato. Bloch and Kato gave a integral refinement of Beilinson's conjecture, and then maybe the conjecture that generalizes all of these in a certain sense, or at least to some extent, is the equivariant Tamagawa number conjecture, the ETNC, due to Burns and Fox. But there are certainly many other people who've made many solid contributions to this field, including Stark, whose conjecture I'm going to talk about for most of the rest of this talk. Okay, so are there any questions so far? Move along. Okay, so now I want to talk about Abelian L-functions, and that's what I'm going to talk about for the rest of today's talk. in fact, for a good chunk of the next talk also. Okay. So let's start with what's called an abelian extension of number fields, meaning a Galois extension. A Galois extension of number fields. Okay, so this has a finite Galois group, and I'm going to assume that it's abelian. Okay, so this notation is going to remain in force for the rest of the talk. Okay, so we take a character of this abelian group, this finite abelian group. Okay, an irreducible character, which because it's abelian will be one-dimensional. Okay. Okay. And then we can define what's called the L function, which is a generalization of the zeta function that I defined, which is going to be the sum over all integral ideals of OF. Okay. You really need to take ideals that are relatively prime to the conductor of this character. So this character has a certain ideal called its conductor, which I won't define, but you can take chi of what's called the Frobenius associated to that ideal, divided by the norm of ideal to the s. Okay, so let me just say, in the case when chi is the trivial character, so these are all 1, and then you get the sum of 1 over norm of a to the s, you get exactly the Dedekind zeta function of f that I defined before. So this is a generalization of that, where you introduce the values of a character. Okay, so sigma a which is called the Frobenius associated. Okay, so this is some element of the Galois group of k over f. Okay, so it makes sense to take chi of it. Okay, so let me actually, before I move further, just give the simplest example of this. When f is q, this character is called a Dirichlet character, and the associated L function is called the Dirichlet L function. So let me just make that more explicit, okay? Without getting involved in what this Frobenius means, let me just give a concrete example where it's very explicit about what it means. So we'll take f equals q, and we'll take chi to be a group homomorphism from just z mod nz star. This is a very concrete example of saying what the group is, into c star. Okay, and then L of chi s, okay, is just going to be the sum as n goes from 1 to infinity of maybe take n relatively prime to capital N of chi of n over n to the s. Okay, and this is called a Dirichlet L function. This is just a simple. So this is just the example of that abelian L function when f equals q. Okay, because the finite abelian Galois extensions are basically quotients of this z mod nz star. Okay, so now you can ask, what's the leading? So this is just the example. Now, even in that general case of the abelian L function, you can ask, what's the leading term? So what's the generalization? And the Taylor expansion of L of chi s at s equals 0. Okay, and surprisingly, the answer to this is not really known in general. Okay, but one thing at least we know is we can say what the order is of L of chi s at s equals 0. That is known. Okay, so the order at s equals 0 of L of chi s is equal to what I'll call r sub chi now, instead of just r. It depends on chi. Okay, and it's the number of Archimedean places V such that the value of chi on the Frobenius of that Archimedean place is 1. Okay, so there's a Frobenius associated to an Archimedean place as well as there is to a finite place. And the number of the places such that chi, the associated Frobenius, is 1. That is known to be the order of vanishing at s equals 0 of this Abelian L function. So now this might not be exactly correct in small cases, like if chi is the trivial character, then it's maybe that minus 1 or something. So maybe I should say chi non-trivial. And then, I mean, it's known what it is when chi is trivial, but let's not deal with it because we've already discussed the chi trivial case. That's just the Dedekind zeta function. Okay, so, right. So maybe I can say what that Frobenius is, by the way, while I'm erasing. If you have a complex place, that Frobenius is just defined to be trivial, just the identity. So there's nothing there. So it automatically gets counted in that count. And then if you have a real place, the Frobenius is just given by the complex conjugation. Okay. Okay. So now I want to answer this question in a case in which it's known. There are not that many, but let me just tell you in a case where it's known, which is the case of a Dirichlet character. So this is a general question you can ask, and this leading order of vanishing is known in the general setting, but the answer to the question of what's the leading term is not known in very many cases. So in the case when f is q, we're just going to work it out together from scratch somehow, and from some classical formulas. We're going to get the answer to see what we should expect in the general case. Okay, so the case that I want to do is the case when chi of minus 1 is 1, because this is more interesting than the other case. Okay. So minus 1, chi of minus 1 corresponds to this chi of sigma v. So this corresponds to the r chi equals 1. In the other case, when chi of minus 1 is minus 1, then r chi is 0. Well, okay. So all right. So there's what's the situation in terms of the number field in this case? I didn't really mention. Well, the group that has that Galois group is Q adjoined zeta n. Q adjoined the nth roots of unity. And chi is actually factoring through the subfield of index 2 in here because chi of minus 1 is 1. So it factors through this field, often called Q adjoined zeta n plus, which has index 2. So chi is really a character of this Galois group, which is z mod n z star mod plus or minus 1. That's the Galois group of this extension. Okay, so that's the field picture that's showing up here. So what is L of chi s? Okay, so that is the sum of chi of n over n to the s as n goes from 1 to infinity, as long as they define chi of a to be 0 if a is not relatively prime to n. So this can be written in terms of the Hurwitz zeta function. Okay, so this can be written, and I'll define the Hurwitz zeta function in a second, as the sum as a goes from 1 to capital N of integers that are relatively prime to n of chi of a. So I'm grouping terms together that have the same chi value. So I'm grouping over the residue classes mod n times the Hurwitz zeta function of a over n comma s. Okay, so this Hurwitz zeta function is some generalization of the Riemann zeta function. Okay, so this is just the sum as n goes from 1 to infinity of 1 over x plus n to the s. So when x is 0, I guess that's the just the usual Riemann zeta function. Okay, so this converges for x and s and c, real part of x greater than 0, real part of s greater than 1. Yeah. Okay. So now let me. So this is a simple just change of variables. You see, just grouping together the terms that appear here by what they are mod a, then you can see you get that formula. So now what I'm going to do is look at the value of this at s equals 0. Okay. So. Okay, so now we want the Taylor expansion of zeta, of the Hurwitz zeta function. Okay, so it turns out that this is, so 1/2. So I got this formula from the ultimate reference for these kinds of things. Does anyone know what the ultimate reference for these kinds of things is? Wikipedia. So I got this formula from Wikipedia. So you take log of gamma of x minus 1/2. Okay, so here's the Taylor expansion of this at s equals 0. So it starts with this constant plus s times this plus dot dot dot. Okay, so now chi of minus 1 equals 1 implies that, well, chi of, and when I'm taking this sum here, I can group together a and n minus a, because chi of n minus a, so chi of a value only depends on what it is modulo n, so that's the same as chi of minus a, right? And since this is a group homomorphism, so that's chi of minus 1 times chi of a, which is just chi of a, because chi of minus 1 is 1. Okay, so I can group together the terms, so I combine terms for a and n minus a. Okay, so then if you do that, if you add the constants, then you get 1/2 minus a plus 1/2 minus n minus a, over n, and that just cancels out. Okay, that just, so constant, you get 1/2 minus a over n plus 1/2 minus n minus a over n. And that's 0. Okay, so if I add this expression for a over n and n minus a over n, then the constant term is 0, which is good, because remember, this thing is supposed to have a 0 at s equals 0. Our chi is supposed to be 1, okay, in the case when chi of minus 1 is 1. Okay, and so now we care about the coefficient of s. Okay, so then you just look at this thing and you add together the terms that you get. You get log of, well, you get gamma of a over n and log of, gamma of 1 minus a over n, okay, over 2 pi, the 1/2, there's 2 of them, so it just becomes log of 2 pi. Okay, and again, Wikipedia will tell you the formula for gamma of x times gamma of 1 minus x, that's something. In terms of sign, you get, and you put it all together and you get minus log of 2 times sine of pi a over n. Okay, and I want to write this in a particular, slightly different way. That's maybe slightly more suggestive, using sort of the half-angle formula for cosine, which is, I can write this as minus 1/2 times log of 2 minus 2 cosine 2 pi a over n. Okay? So now I'm going to call the thing inside that log, I'm going to call that U of A. Okay, so U of A, it's going to call that 2 minus 2 cosine of 2 pi A over n. Okay, so this can be written as a certain product, 1 minus zeta n to the A times 1 minus zeta n to the minus A, which is some element of Q join zeta n plus. Okay, so where, right, so this is 1 minus, wait. I hope what I'm right. Yeah, this is right. Okay, yeah, where zeta n is e to the 2 pi I over n. Okay, so if you just work out this, it turns out this equals this. You get 1 from this two products and another 1 from the product of these two, and then the cross terms gives you this thing plus its complex conjugate, which is basically twice the real part of this, which is exactly this. Okay, 2 pi. Yeah. Okay. All right. So that's interesting. Okay. So this is called a circular unit. Or maybe a cyclotomic unit. Maybe really to make it a unit, it's better to divide out by 1 minus zeta n, or 1 minus zeta n squared here, and you can get an honest unit, but I'm not going to be too nitpicky with the terminology. We'll just call this our circular unit. It's basically, if n is not prime, I think it is basically a unit in the ring of integers, this number field. So the summary is that L of chi at 0 is just 0. That was the constant getting 0. And that L prime of chi at 0, that's the leading term, is equal to negative 1/2 times the sum, as A was in this Galois group, Z mod n Z star mod plus minus 1, of chi of A times log of U of A. Okay? And U of A is a unit at least away from n. So it's in this number field, Q joins zeta n plus. Okay, now if I invert n, then it really is a unit. And I think it is a unit without inverting n if n is not prime, or not a prime power at least. Okay, so in the last 10 minutes I just want to now give the generalization of this statement. So this is the motivation for what we expect in general. The leading term of our Abelian L function at 0 should be some like twisted trace, essentially, some sum of chi of A times log of units. Okay? Or in general you're going to have determinants of units. Like a regulator, like we saw for the Dedekind zeta function, the Dirichlet class number formula gave us a regulator. So that's exactly what Stark's conjecture says, is that we should get the same formula that we got for the Dirichlet class number formula, except we get some twisted trace of these guys given by summing over chi of elements in the Galois group. Okay. So now let me state Stark's conjecture. Okay, so the setting for Stark's conjecture is let K over F be a number field, be a finite abelian extension. Of number fields. Okay, and let chi be a homomorphism of this abelian group, the finite abelian group, which is the Galois group, to some field E star. Okay, and where E I want it to be just a number, the smallest number field that you need in order to have chi defined. Okay, so it's some subfield of C. Okay, and let's assume for simplicity that chi is not 1. So in the case chi equals 1, we know what's going on. That's just the Dedekind zeta function. Now we define the chi component of the units to be, well, you tensor with E in order to have the values of the character chi appearing. And you want to take the chi inverse component. So this is the set of elements, okay, U in this tensor product, such that the Galois acts on it. So Galois just on this tensor just acts on the first coordinate. Okay, just acts on OK star, such that this is equal to U to the power of chi inverse of sigma. So what does this to the power of that mean? Well, this is a number that lives in E, and it just means multiplying on this tensor factor with E. So this is a tensor product over Z, where the group here, operation here is multiplication, and here it's addition, so it's kind of funny. But so I just mean if you have an element, you just multiply in the tensor on the right by the value of E. Okay, but really you should think of that as raising to the power. And in fact, if chi was a quadratic character that took the values plus or minus 1, I wouldn't need this tensor with E, and I could really just write this expression this way, because this would be plus or minus 1, and it would make sense. The point of the tensor is just to allow you to make sense of expressions of that form when the character does not take values in the integers. Okay, so this is a sigma for all sigma. Okay, so that's the unit group that's going to play a role. So you see, if I just take this sum, or maybe you should write the product of U of A tensor chi of A, that would be a generator of this group in the case, in that case. Okay, so it is known that the rank of this group, or I should say the dimension as an E vector space of this U chi, is the thing that I wrote down to be R chi before. Okay. So now we're going to take a basis of this E vector space. And the leading term is essentially going to be the regulator of this basis. So conjecturally, so let U1 through U R chi be a basis of U chi, be an E basis, E vector space basis. Okay, and for each of the places, the Archimedean places that gets counted in this count for R chi, okay, so for each Archimedean place V, such that chi of sigma V is equal to 1, okay, let W be a place of K above V. Okay, and then we can extend the map, U going to the log of the absolute value of W of U, right? So this is a map from K star to R, okay, to an E linear map from U chi to C. Okay, so U chi. So basically, I just take log absolute value of the thing in this coordinate, and then I multiply it by the value E. E is a subfield of C. Okay. Okay, and then finally we define the regulator of chi, to then be the determinant of the log of the absolute value of Wi of U chi j. Okay, as this matrix as I and j go from 1 to R chi. And maybe to make it, okay, so it's not quite well defined, because Of course, you can order these things, but also this is just an E basis. So it's well defined up to, I guess, an element of E star. Okay? So Stark's conjecture is basically that is the leading term of the L value up to, the ambiguity that it has in its definition, namely multiplication by an element of E star. Okay, so Stark's conjecture is that the leading term of chi at 0, because I said we know that it has an order of vanishing r chi, the leading term is this r chi, up to multiplication by an element of E star. So I'll just call that C chi. Okay, and that has to be there because I've only defined it up to multiplication by E star. Okay, for some C chi and E star. Okay, now this can be made more precise. This E star ambiguity can be made more precise, but I won't say anything about that now. Okay, so in the example that I gave before of a Dirichlet L-function, f equals q, okay, the u chi is just the thing that's made out of the ua. So it would be the product as a goes from 1 to n of a relatively prime to n. Actually, I don't want to do it that way because I want to take pairs. So I'll take a and z mod n z star. So I group together a and minus a, remember? So it was just this ua that I had, u of a. This unit, okay, tensored with chi of a. And Galois acts by, it acts by chi, or chi inverse, I should say. Okay, so that was my u chi. Okay, and so that's basically all I wanted to say in the last maybe minute that I have. I want to say a little bit about what's known. Well, first let me say that this can be made more precise. So in particular, Rubin has an integral version. So already in Stark's conjecture, you can make the E a little bit more precise. Okay, you can see how Galois acts on the E. But even beyond that, you have an integral refinement due to Rubin. Okay, and you can also say that it can also be even very explicit, can be made precise, or very precise, so without this ambiguity nonsense, when r chi equals 1. Okay, and then the last 30 seconds, let me just tell you what's known about it. Okay, so known cases. So the first is f equals q. We just worked that out today. We did that in the lecture. Okay. So this is the theory of circular units. So in the same set of papers where Stark presented the conjecture, he proved it for quadratic imaginary fields. Okay, so e.g., quadratic imaginary field is a degree 2 extension of Q. That's given by adjoining a square root of a negative number. So this is through the theory of elliptic units. So these are generalizations of these circular units using special values of modular forms. And then the last thing that I want to point out, just because it's very relevant for the direction I'm going to go with the sequence of lectures, is in the case when chi is any quadratic character over any ground field, okay, i.e. when k over f has degree 2. And the way that you prove it is that there's a factorization formula for zeta k of s when it's a degree 2 extension, that this is equal to zeta f of s times the L function that you're interested in. Okay, there's a generalization of this factorization formula, but in the case where you know everything except what you want, name L of chi s, that only happens when it's degree 2. Then you have this factorization formula, and somehow you know the leading terms here and here by the Dirichlet class number formula, and that implies Stark's conjecture. So Dirichlet class number formula for zeta k and zeta f, they imply Stark's conjecture for L of chi s. Okay, and so this was worked out by Jonathan Sands. So this kind of idea of using a factorization formula where you know sort of two sides and use it to figure out the last is something that I'm going to get back to in my third talk. Okay, thanks a lot.